So first of all, we've talked a lot about restrictions already in this course. And for logarithmic equations, there certainly are restrictions. So what I'm going to start with is I'm going to start with this log base A of B equals C. Okay? And I can rewrite that as A to the C equals B. Right? And I'm just going to, as sort of an extra part of this, write them out as functions. So y equals log base A of x, and y equals A to the x. So in the top one, x is like the b, right? It's log of x, it's log of b, and the c is like the y. This is going to help in a minute. And in this case, the c is the x and the b is the y. That might be helpful in a minute to sort of think about what goes with what. And hopefully I know we have done very little graphing of logarithmic functions, but you should be familiar with the graph of it as well, for sure. So what does a graph of a logarithmic function look like? It looks like this. Okay. And what does a graph of an exponential equation look like? Depending on the transform, whoa, that's terrible. Depending on the transformations, there we go, that's a little bit better, still pretty bad. It looks kind of like that. Okay? So what we can do with all of these 6 little statements or sketches, what we can do is we can think about what are the possible values for A, B, and C. The A, B, and C over here are the same A, B, and C, right? This A is the same as this A. The base doesn't change. This C is the same as this C, because I rewrote this line. The x's and y's are different. I wrote them as functions in this case. So the x's and y's might just help us think about the a's, the b's, and the c's. Are we okay with that? So what are the possible values for A, B, and C? Like, what are restrictions that we need to put on these things? What is A never allowed to be? What is B never allowed to be? What is C never allowed to be? How can you look at those 6 little blurbs and determine what the possible values for these things are? Yeah. A can't be negative. Why do you say that? Very good. A can't be negative. So the base of it, when we were talking about exponential functions, was it, or logarithmics, both kind of thing? Yeah. And if you think about if you're more familiar with the exponential function, what if I put a negative value in for A? And I start changing the x's. So I get A to the 2 is positive, but A to the 3 is negative, A to the 4 is positive again, A to the 5 is negative again. That's not a function. It jumps around. You can't draw a smooth, there's no smooth curve that goes through that. It's not a function. So A has to be positive. Very good. That's one of our restrictions. Anybody have another one? Megan? Yeah, A can't be 1. A can be 1, but it won't be logarithmic. It won't be as interesting. But mathematically, it'll work. But you're right, it's not going to be logarithmic. other ideas? Where do those graphs never go? Where does the top graph never go? Look at this graph. X is always positive. Y can be anything. It's going to go down forever and it's going to go up forever. But it's never going to touch 0 and it's never going to be negative. So the x value of this, x, is always positive. What does x coincide with over there? John? B. Look at this one. This one, y can never be negative. Right? X can be anything. X is going to go this way forever. X is going to go that way forever. It's going to go up forever. So y will always be positive. It can be any positive number. It won't be 0. But y can be never be negative. What does y go with over there? B as well. Right? And so B can also never be negative. B will always be greater than 0. And we talked about this possibly briefly, but when you start putting negatives into the base of a log or the argument of a log, you start to get, like, strange things start to happen. So there is mathematics that can do that, but we don't know it, and it's a different kind of mathematics. And so for us, we kind of go with the rule that A is always negative, always positive, A is never negative, and B tends to not be negative as well, kind of thing. So we sort of go with these two restrictions as a general rule. But I say this loosely because there are a couple of these little quirky times where it sort of looks like it's negative and it works out. Like there's a couple, but don't worry too much about that. They'll come up a little bit and we'll talk about it, but it's not something you really need to worry about for like assessments, that kind of thing. But so it's like we have these restrictions, but in our back pocket we kind of know that they're sort of strange restrictions, sort of looser restrictions, but for us they are the restrictions we're going with 100% absolutely for solving these equations. Okay? What was I going to say? If A is always positive, B will also always be positive. Like when I do -3 cubed, I get a negative value for B, right? But remember, we already made the restriction that A has got to be positive. So if I take any positive number and I raise it to an exponent, the answer will always be positive. It has to be. That's, again, something you should be able to think through and understand, right? So the relationship between A and B, if one's always positive, the other is always going to be positive, kind of thing. Like that's fair, that's going to work out. Okay, so restrictions on the base of a logarithm in particular, we can use the exponential notation to help us understand this, but really what we're looking at is for logarithms. The base of a logarithm and the argument of a logarithm both always have to be greater than 0. Okay, let's start solving some equations. And again, I've said this before, one of the hardest parts of these logarithmic equations and all of this unit is probably figuring out how you do which type of question. If you mess up the types and you try to solve one like a different one, it's not going to work. Okay? And it is, once you get it, it is clear which type is which. Like it shouldn't be unclear, but if you haven't done enough practice, then that's when it becomes unclear. That's when it's not, when you can't tell which type is which. So in this case, my restriction is going to be x plus 1 is greater than 0. Restrictions only matter where the x is. So remember, the base of a log has to be greater than 0, but the base of the log is 3. It is greater than 0. Like that, well, there's no restriction there, right? Don't start saying 3 greater than 0. Well, yeah, that's true, but that's not what we care about. But the argument of a log has to be greater than 0. Do you agree? That's what we just talked about. So x plus 1 has to be greater than 0, which means x has to be greater than -1. I move the 1 to the other side, so this is my restriction. In this case, it turns out that's not a very useful restriction. Nevertheless, it's just good habit to do that in the beginning Otherwise, we get to the end of a question and we forget to look back or that sort of thing. How am I going to do this one? This one's kind of easy because I could just rewrite it in exponential form. And that's what I would do. So this one's going to be 3. I'm going to start with the x part. This one's going to be x plus 1 equals 3 squared, right? So the base stays the same. The result of the log becomes the exponent, 3 squared, and the arguments of the log becomes the result. And so then x plus 1 equals 9, and x equals 8. Is 8 greater than -1? Yes. So we're fine. Usually these questions work out fine where the restrictions are relevant anyway. That's not the kind we're worried about, but I wouldn't, if I were you, try to memorize when you need to worry about restrictions, when you don't. Just do them every time, and then, then you never have to worry about that part. Okay? Everybody okay with that one? The next one, what's my restriction? My restriction is x has to be greater than 0 because I've got x in the base. And again, I'm going to rewrite this one in exponential form. Okay, because it's a single log. This is the kind of thing. It's log base something of something equals something. I can rewrite that in exponential form. And often, see what I mean when I said before about, you need to be able to do this. You need to be able to rewrite, because even when we're solving these things, we're rewriting things in exponential form 100%, or exponential stuff in logarithmic form. We go back and forth constantly. You need to be able to do this. And if you're good at doing this, it'll help that you'll know this is what you're supposed to do in a question like this. You'll see, you'll be like, oh, that question is saying x squared equals 16. I can just solve that like that. Is there another way to solve a question like this? Probably. There's usually lots of ways to solve log questions. But to me, this is the easiest way. And if you're good at rewriting back and forth, you'll see that. What am I going to do now? Take the square root of both sides, and I get x equals positive 4 and x equals negative 4. Usually, we would write that in as x equals plus minus 4. So you could take a step and do that if you want. But ultimately, I want to write it out twice. Why? Yeah, so then we have a solution that's extraneous. Because in my original line, I can't have a negative base in a logarithm. But I rewrote it in a way that was convenient for me. And when I did that, I caused more solutions to come out. Okay, so this is another one that it's just a single log, so I can rewrite it in exponential form. We're gonna solve this 2 ways just to demonstrate that again there are different ways of doing these things, and you can decide which way you like best. So when it just says log, what is that telling me? Cassidy? Base 10. So that means that x cubed, the base stays the same, so the base is 10, and 9 is the exponent. What is the cube root of 10 to the 9? If you want to see this with an extra step, you wouldn't have to show this step. But really, when I'm taking the square root of both sides, or when I'm taking the cube root of both sides, what I'm actually doing is I'm raising both sides to the exponent 1/3. So if I raise both sides to the exponent 1/3, I get 3 times a third, which is x, and I get 9 times a third, which is 3. So I get x equals 1,000. And I'm done. Oh, forgot my restriction. Nobody reminded me. X cubed has to be greater than 0. Take the cube root of both sides. X is greater than 0. It's not relevant. The reason why I forgot is because it doesn't matter in this question. But again, that's not a good habit to be in. Okay? It's a little bit more complicated than whenever I get a negative answer, that's probably not going to work. Unfortunately, that's not really how this works. It seems that way, and so I think it's easy to get in the habit of not worrying about restrictions, and if you get a negative answer, just check that one, but that doesn't always work that way. And you'll see as we get through this why that's the case. Okay, so how else could I have done this? I could take the 3 out front. 3 log x equals 9. Divide both sides by 3 log x cubed. Log of x cubed equals 3. X cubed equals 10 to the 3. What have I done wrong here? I wrote it in, but I already used it. Thank you. Okay. I was going to say, this isn't working out to the same answer. Something's wrong here. X equals 1,000. I wrote it in after, but I already took it out, so I didn't need it there. Okay, so I took the 3 out front, so it's just x, but I get the same answer. So I don't know. Either way works. There is one case, though, when the exponent is an even number. So if it's x cubed, it works fine. If it's x squared, it's a little quirky. Because if I do it one way, I get one answer, and if I do it the other way, I get 2 answers. And you have to say which one is the correct solution. So that can be a little bit quirky, but again, it's not something we really need to worry too much about. Okay, so that's sort of one type of question where, well, we're doing another couple of examples sort of similar, but or at least one more example that's sort of similar. But one type of question where you can just rewrite it in exponential form. Actually, I'm not sure if we're going to do any more like that. This one's a little bit different. Okay, so I'm going to do my restriction. X has to be greater than 0 because it's in the argument of the log. Both of these are to the same base. They're base 10. So it turns out that this is very similar to the grade 11 kinds of questions. That if you have an exponent or a power on both sides with the same base, you can equate the exponents. So that would be something like 3 to the x plus 7 equals 3 to the 79. Then x plus 7 equals 79. If the bases are the same and I don't have other junk, I can equate the exponents, is what we call that. So this is very much the same. The bases of the logs are the same. So I can equate the arguments. I got to do one step before I do that because of that half. I do have some other junk. So this is log of 16 to the 1/2, or the square root of 16. You can write it however you want. Right? So I need to handle the other junk first, but then I can say, therefore, if the log of x equals the log of the square root of 16, then x has to be equal to the square root of 16. And the square root of 16 is plus or minus 4, so x equals 4 and x equals negative 4, but we had a restriction of x has to be greater than 0. So again, this is extraneous. Yep. You have to say something. So extraneous, sometimes I think in the solutions in this unit, it says not in the domain. If you think about the graph, you can't put negative values in for x of the graph of log, right? So not in the domain, sometimes we say, or extraneous. Sure, why not? Let's make it ext, okay. So next one, very similar. Oh, our restriction, x plus 7 greater than 0, x greater than negative 7. So in this case, x could be a negative value, right? It's not just when x is negative. Like x negative 3 would work. X just has to be bigger than negative 7 because the whole argument has to be bigger than 0. But x itself could be some negative numbers. So what I'm going to do here is the same thing I did last time. I can if it's log base 2 of something equals log base 2 of something, the somethings have to be equal. So therefore, this is a really easy question. X plus 7 equals 4. You just have to notice that it's this kind. And x equals negative 3. Again, that's fine. Fits our restriction set. There's no worries there. It's negative, but it is greater than negative 7, so I'm good. Okay. You could also have done this one like this, although I don't know why you would. It's a lot more work. Log base 2 of x plus 7 equals... See, this is where if all you know how to do is evaluate logs by rewriting an exponential form, you can't do that when it's in an equation. In this case, we don't have to because we have the easier way of doing it anyway, but you see what I mean? Like, we have to be able to evaluate logs as they are. Oops, so this is like 2 squared. So this is log base 2 of x plus 7, which equals log base 2 of 2 to the 2 is 2. And then I rewrite this in logarithmic or in exponential form. So I end up with x plus 7 equals 2 to the 2, but I just end up with the same thing. Oh my gosh, like what a whole bunch of extra work for nothing. Yes? Yes. And that's just like grade 11 when you're doing that with exponential equations, right? And we've done a little bit of that this year as well. Do you see the parallel there? Because I did go over that quickly, I know, but it's the same idea. But only when you have a single log on both sides, okay? And only if the bases of the logs are the same. So we did a couple of examples like that, but those are the kinds where you can do it. We're going to see new kinds coming up that you can't. But look for this one, look at how many more steps that was. It was a disaster, but it did work. So however you see it is fine. Both would be totally fine, but this is an easy question if you do it that first way. So now we start getting into questions that have multiple logs in them. And it gets even more complicated, but which type is which? I suppose one way that you could tell the difference. So take a look at this question. Hopefully you've written it down. There's one x in it. There's only one x. Look at how that's different from this question here that has two x's in it. So question G that we're going to get to in a moment is very different in how we solve it. And you'll see in a minute from question E and all the ones above it. Okay? And again, the ones above are even more different because there was only two logs. This E, I guess, is a bit more complicated version of the ones above. What I'm going to do is I'm going to get I'm going to get log x by itself and put everything else together and try to simplify. So I'm going to get log of x equals 2 log 5 plus log 3. And I'm going to start simplifying the right side. So log of x equals log of 5 squared plus log of 3. Does anybody know what I can do here? These are the properties that we worked on, yep. Very good. So log of 25. And because I'm adding logs with the same base, I can multiply the arguments. 25 times 3 is 75. Therefore, x equals 75. And I'm done. Right? That's what, Megan, that's what you just asked about. Same base on both sides. So I can equate the arguments in this case. Yeah? Sure. Yeah. So that, to me, is similar to the ones above, but had some work to do first. And again, you could get it confused because the next questions that we're doing down below have multiple logs in them, but they also have multiple x's, and that's what makes them different. One more type I want to do because I feel like it can throw people for a loop. There's one like this in the practice. Same idea. I don't know if you even have to write it down. You can find it online later if you want to just watch. I'm going to do it quickly because I want to get to the more interesting ones. Log of the square root of x. People will get thrown because, oh my gosh, there's a square root, but it's really just the same. Log of 10. What do I do when I'm subtracting logs? I divide. So this is log of 9 over 10. That's the properties that we've done over the last couple of days. Therefore, the square root of x equals 9 over 10. And how do I solve this to find x? This is from grade 9. I square both sides. X equals 81 over 100. But the problem is, like, when you watch me do it, and I get you through the first steps and tell you which kind it is, all those steps look pretty easy. You're good at this stuff now. Like, you're getting logs. Probably a lot of people are really clicking. They're like, hey, I can do this stuff. This is good, right? And then all of a sudden, there's a worksheet, and they're all muddled together, and you're like, oh my gosh, which one's which? And it starts to get overwhelming, right? So it is tricky. Look for those little steps. It's a big part of what you're practicing, I think. Those little hints and indicators about how you solve which type. All of those ones above only have one x in them. Okay, so that makes them a little bit more straightforward. Then we get to these kinds that have multiple x's in them. This is a new kind, sort of. Does anybody notice anything about these that might be relevant? Might help us, John? Very nice. What else? Anything else? Ooh. So I'm adding logs in the same base, so I can say that again? I can multiply the arguments, which is multiplying the brackets. And very good, that's exactly what you do. So I go log base 5 of the whole thing of x plus 1 times x minus 3 equals 1. If I had a whole bunch of other junk, if it had x's, I'd keep it with the x side. If it didn't have x's, I'd toss it to the other side kind of thing, right? Like, you're still going to do that. In this case, in a lot of these questions, since I don't have logs on both sides, I only have one log, I rewrite in exponential form. So that means the argument of the log, which is x plus 1 times x minus 3 equals 5 to the 1. Now this is a grade 10 question. Everything comes back to grade 10. X times x, so then I expand the left side. So negative 3x plus 1x is minus 2x minus 3 equals 5. X squared minus 2x minus 8 equals 0. Oh dear, we forgot something. X minus 4, x plus 2 equals 0. See, bad habits. And this is interesting. So before I move on, I'm going to go back and do my restrictions. Put your pencil down and watch. My restrictions are x plus 1 greater than 0, which means x is greater than negative 1, and x minus 3 greater than 0, which means x is greater than 3. So what can I conclude here? Oh, well, I don't know about that yet. Even just looking, you might be right, even just looking at the restrictions. What can we see? If x has to be greater than negative 1 and x has to be greater than 3. Very good. It's not like one has to be greater than one of them and the other has to be greater than the other. No. A solution has to fit both restrictions. So it turns out that one's irrelevant, and this is the only one that we actually care about. If x has to be greater than both those things, it only has to be greater than this thing, and it will automatically be greater than the other. Okay, good. Now I can go back to the other one. So I get x equals positive 4. Looks like that one's going to be okay. X equals negative 2. That one's not. That was a solution to the quadratic part, but not to the original question. If I put -2 in here, actually in either of them, I get a negative argument, and that doesn't work for logs. Okay, and now we're just going to do a few more kinds of questions that are similar to that type. We'll do as many examples as we can fit in here. There's only a couple more, I think, anyway. Try the first step of this one. This one's very similar, like the way it kind of comes out in the wash is a bit different, but yes? Say that again? No, they do have restrictions. Just like I said, bad habits, they turn out not to be relevant, so I didn't worry about them. But this one, x has to be greater than 0, and the square root of x has to be greater than 0. But both of those are fine, right? They work out. In these kinds of questions, like every time or almost every time or really every time, you get two answers and one of them will be extraneous. So the restrictions are super important in these kinds of questions. But in the ones above, like it only matters in a couple of certain cases. But for your habit, it's better to always worry about them. So then you don't have to decide when which is which. Okay, so let's do those restrictions on that topic. X is greater than 0. And x minus 6 is greater than 0, which means x is greater than 6, which means that's the one that I care about. The other one doesn't really matter. You don't have to cross them out, like you don't have to do it that way, but you got to write in those restrictions so that you make sure you think about it. So what's the first step of this question? Does anybody see it? You should be able to compare it to the last example and try to do the same thing. So it should look like this. Log base 4 of x times x minus 6. So the last one had two binomials. This one's got a binomial and a monomial, but that doesn't matter, right? That part doesn't really matter. Equals 2. Rewrite in exponential form, x times x minus 6 equals 4 squared. X squared minus 6x minus 16 equals 0. Go ahead and solve. Questions so far? Yes. Yes. We're rewriting it in exponential form. Think about it like this. Log base A of B equals C. So there's my A, this whole thing is my B, and there's my C. And that means A to the C equals B. Right? I know, it's weird, like, because you're really good at that now, but it's a bit stranger when all of a sudden there's other junk in. But once you practice that a few times, I don't think that'll be the hard part of these questions. In fact, most of these questions aren't really that hard once you get the steps, because it's just solving a quadratic. Oh my gosh, right? But the hard part is knowing what to do, what's type of question, that sort of thing. If solving a quadratic is the part that we're struggling with right now, we're in a lot of trouble. So same thing, I'm going to let you try this one. When we get to this point, I did my restrictions. Okay, x greater than -2 and x greater than -3 means x has to be greater than -2. When we get to this step, there's two ways that I could do it. One way is I can evaluate this. What is log base 2 of 1? 0. Very good. And then I can rewrite an exponential form. It'll be 2 to the 0, right? When I bring this base, I'll raise that 2 to the exponent 0, right? And what's that going to give me, though, is the same thing as if I just realized that I can equate the arguments of both sides, because both sides are log base 2 of something. So those somethings have to be equal. So either way, I work my way to this step, whether it takes me 1 step or 2 step or 3 steps, I end up with that, right? Because 2 to the 0 is 1 anyway. So it really, like, same thing. So then I get x squared plus 5x plus 6 minus 1 equals 0. X squared plus 5x plus 5 equals 0. And does anybody know what we should do now? John? See if it's factorable. How am I going to do that? Discriminant, very good. B squared minus 4ac, so that's 25 minus 20. In fact, I can do that in my head, right? 4 times 5. So 25 minus 20 is 5. Okay. And what does that tell me? If the discriminant is 5, not factorable, but solvable. So don't say no solution. There certainly is a solution to this. How do I get it? Quadratic formula, something we haven't seen in a little while, because we kind of skipped it in the last unit, although we could have used it. So -5 plus or minus the square root of 5 squared minus 4 times 1 times 5. There's that discriminant over 2 times 1, which equals -5, which equals x equals, -5 plus the square root of 5 over 2, and x equals -5 minus square root of 5 over 2. And then we have to check those in our restriction set, and both of them are negative, and it's kind of nasty too, this one. If you check them on your calculator, you will notice that this one is a little bit smaller, which you would expect because it starts as negative and you're subtracting, and it turns out that that's extraneous. Okay, one more question. This one's a little, where did it go? Down here. This one's a little bit different because I've got 3 things. We only have a couple of minutes here, so I'm going to go through this quickly because it's just the last little step that you probably are too worried about. So we do log base 3. I can multiply those arguments because we're adding. Oops. So I get log base 3 of x minus 1 times x minus 2. And what did I say before about in general? You want to get all the x's to one side and all the other junk to the other side, whether it's log or not. So I'm going to bring this log to the other side and subtract it. Log base 3 of x plus 3. And that's going to be equal. What is going on here? X plus 3 equals log base 3 of 3. I'm going to say that equals 1 right now, because why not? Stop it. Okay, and now I'm subtracting logs of the same base, so I can divide, because I do have to collect everything together. I can't take the log of both sides or the reverse log of both sides until I get everything together. So I get log base 3 of x minus 1 times x minus 2 all over x plus 3 equal to 1. I don't know if it was better to do it equal to 1 or not in this case. Probably not, but it doesn't matter. So then I rewrite and I get x minus 1 times x minus 2 all over x plus 3 equals 3 to the 1, which is just 3. And then what do? I solve it like a rational equation, oh my gosh, from the last unit. Now, not the inequalities. This is an equation. So I end up doing x minus 1 times x minus 2 equals 3 times x plus 3. And I collect everything to one side. I end up with a quadratic, and I just solve it. So this is x squared minus 3x plus 2 minus 3x minus 9 equals 0. X squared minus 3x, minus 6x minus 8 equals 0. Is that, 7, sorry. X minus 7, x plus 1 equals 0. X equals 7, x equals negative 1, and one of those is in my restriction. Oh, I didn't do my restrictions, but it turns out to be this one. So I was rushing too much. I almost beat the bell. Extraneous. So those questions, here's the practice. Those questions are very similar. It's that last step that I know it can be a bit tricky, but otherwise it's the same idea, same general